So welcome to the HAO colloquium. And today I'm really happy to introduce the speaker, Professor Chatterjee from Indian Institute of Astrophysics at Bangalore. Piatti her PhD in physics from the Indian Institute of Science, Bangalore in 2007. For her PhD work, she did important work on flux transport dynamos and solar cycle prediction. And subsequently, she has held postdoc positions at several places, including the Tata Institute for Fundamental Research at Mumbai, Nordita in Stockholm, and from 2012 and 2014, she was a postdoc fellow at HAO Boulder, and then at the University of Oslo. And since 2015, she has joined the faculty at the Indian Institute of Astrophysics. Piatti's primary research interest is in the application of computational MHD study of the sun from the solar interior to the corona, including both quiet sun and solar eruptive phenomena. Some of her recent work has been including understanding how delta spots form and generate repeatedly flares, and also demonstrating the 4 ingredient criteria for the generation of solar spicules, which is published recently in the Nature Physics. And lately, her interest has also diversified into other astrophysics MHD domains, including compact star dynamos and accretion disks. Piatti is an expert user and one of the developers of the open source parallel radiated MHD solver, the Pencil Code. She also serves on the International Pencil Code Steering Committee since 2019. She has incorporated many new and insightful modules in the Pencil Code to make this MHD code more realistic and can be forward modeled to compare directly with many solar observations. Today, she will talk about her recent MHD simulations of solar spicules and draw parallel between solar plasmas radiated with magnetic field and polymeric fluids. So, yeah.
Thanks a lot, Jihom, for the very kind introduction. And I'm really very happy to be back in HAO after almost a decade. And thank you, Jihom, for inviting me here. So basically, in this talk, I would like to present our latest work. So, which was, here is the team that was involved in this work. So Shoaib is my PhD student, and there are the other people, all the other people here, except for Murthy here, who is a condensed matter experimentalist. All of us are solar physicists. So Murthy is basically responsible for the laboratory experiments on polymeric fluid jets, and we would like to establish this new connection between spicular jets and polymeric fluids in the laboratory. So just before that, a little bit of geography, from where I come from. So our headquarters of IIA is at Bengaluru, and we basically operate several field stations, several optical and radio observatories from there. And the oldest one being the Kodaikanal Solar Observatory, which will complete 125 years next year. And this basically has century-old archival sunspot data that is, really great mine of information. And then this Gauri Vidhanu radio telescope, which basically can look at type 2 radio bursts and image the sun and radio. And then there are these field stations in the Himalayas. A notable one is in Merak. So Merak has this lake called the Pangong Sol Lake. The 2/3 of this lake is in China and 1/3 is in India. And if you see this excursion here, so that is where we plan to build a 2-meter national large solar telescope. And it has been funded in principle, but we are still waiting for final cabinet clearances. So hopefully we will soon have solar observatory high resolution, a spatial resolution telescope of our own in the Himalayas. So with that, let me go back to my talk on spicules. So as I don't need to tell this audience that there are millions of spicules on the solar surface, and hence we use the spicule forest, and which have these certain physical characteristics of lengths, widths, and speeds. And the spicules are observed most clearly in the coronal hole region in the solar limb, and they can be observed in several wavelengths, cooler chromospheric lines to hotter transition region, and UV lines. The idea of this talk is basically to find out if there exists, if at all there exists, a mechanism which can assemble this entire solar spicule forest. So we approach it in a slightly different manner. So let me, we were spurred by this visual similarity between chromospheric data from there, where you see these solar spicules, versus you take a petri dish full of paint, and then you oscillate the petri dish and you get these nice jets of paint. So there is striking visual similarity, but the thing is that does the similarity stop at the visual level, or is there anything deeper that we can do with it? And I would try to convince you that as we dig deeper, we actually find that there is indeed some mathematical similarity in terms of the viscoelastic and Maxwell stresses in both systems, and that leads to phenomenological similarity. So if you do parallel experiments in both systems, they sort of have a very similar trend. Now, before we dig deeper, the first thing that any person who studies fluid would do is they will do a scaling analysis by calculating some non-dimensional numbers. So let us look at these two very different systems. So one is the jet in the solar plasma, the solar atmosphere, which is basically being driven by solar convection, which has a typical frequency of 3.3 millihertz, or the 5-minute oscillation mode. Whereas the fluid that you saw this movie of the paint, there we were exciting the petri dish at a frequency of say 30 hertz and at a particular amplitude. So this particular kind of driving is known as the Faraday excitation, and this has been in existence since 1831. So it's known as parametric driving because the driving is of this form A cos omega t. So there are two parameters, the amplitude and the frequency. So now these are the two systems which are being driven, parametrically driven, say, with two different frequencies and amplitude, and the jets have these characteristics. So the width of the jets in the solar spicule versus in the petri dish, and their lengths, the length of the jet and their typical velocities. And from these things, we can compute some non-dimensional parameters, for example, the aspect ratio. And if you compare the aspect ratio of the spicules to the paint jets, they are in the same ballpark region. And there is yet another non-dimensional number known as the Froude number, which basically tells you the importance of the surface gravity in the dynamics of the system. So if you calculate this Froude number for a continuum system, which is the solar plasma, of course, the solar atmosphere doesn't have a surface like in a fluid, so it does not have surface tension. But for a continuum plasma, you can calculate this Froude number, and so you can for the fluid case, and they also are in the same range. Similarly, you can also calculate the ratio of the acceleration experienced by the spicules and the fluid jets and divide it by the local gravity. So in the solar case, G is the solar gravity, the surface gravity of the sun, and for the paint jets, it is of course the Earth's gravity. And for the solar plasma, this acceleration is actually not the acceleration experienced at the photosphere, but rather the acceleration experienced by the chromospheric plasma. So here you see that the acceleration, the relative acceleration, is also in a range that can be compared. So lastly, we can create another non-dimensional number by multiplying the driving frequency, which is in the millihertz range in the convection in the solar convection zone, versus 30 hertz in the laboratory, and multiply it by the lifetime of the jets. So basically the jets go up and they fall back down. So that is the lifetime of the jets. And if we multiply them, that also is in the similar range. So this gives us some confidence about digging slightly deeper into what is exactly happening. So before we do that, let me briefly show you what exactly is Faraday excitation and what the fluid dynamics, what is it basically done in the fluid dynamics community so far. So the Faraday excitation consists of having this vessel, petri dish. It can have any shape, but here it has a circular shape. And then you basically apply this A cos omega t kind of a driving to it. And then this fluid basically experiences, starts, starts vibrating because of what is known as surface gravity capillary waves. So those are excited in the fluid. And this kind of behavior can actually mathematically be expressed in terms of what is known as the Matthew equation, which is a general equation for a damped driven oscillator. So that's also a parametric equation here, where the zeta represents the distortion of the surface of the fluid. Now, what you're seeing is if you increase the amplitude or the frequency, then instead of getting one cell which resembles the shape of the container, you get more and more complex polygonal cells. And that happens because of what is known as resonant mode coupling. So basically there are these more and more modes, which, basically two subharmonic modes can combine to give a harmonic modes, and they can couple and they can break and form these patterns. Now, if you increase the amplitude really, if you increase the amplitude even further, then instead of the cells, you will see that the cell boundaries, they collide with each other and they give rise to these kind of jetting patterns. So this was actually one of our experiments in the laboratory. And after some time, these patterns become independent of the container geometry. So it doesn't matter, what is the shape of your container, you will still get these modes. So the reason you have these jets in the fluid is because the fluid is sloshing around, and then in the process, you often have the surface. The surface represents a singularity like this. So this is known as a collapsing surface singularity. And when that happens, the surface basically wants to straighten up because it doesn't like the cusps. And in the process, it forms a jet. So it is important to remember that this sort of singularity is responsible for formation of jets, because later on we'll again compare it with a similar kind of singularity that also gives rise to the solar spicules. So now, before we go into the solar spicule, the simulations, let me just give a brief introduction to our radiative MHD model. So we basically solve the MHD equations using the pencil board. And for now, for this set of experiments, there is no convection zone. So there is a very thin, thin layer, but there is no convection that is excited there in the photosphere. And our grid resolution is fine enough, 16 kilometers. And then we have an imposed vertical magnetic field. We also have anisotropic thermal conduction along field lines. And we have incorporated semi-relativistic Boris correction, which also has previously been incorporated in other codes by Matthias and also by Yuhong in their respective codes. And then we have, the realistic convection is not there. It will come later. Sorry about that. But we have LTE radiative transfer, and which is coupled with the Shah ionization equation of state. And we also have a sponge layer at the top. So basically, this is our domain. So we have the subsurface, and it extends up to 44 megameters. And the top 16 megameters of the domain is basically a sponge layer where we keep the coronal temperature constant. And it basically, the job of that sponge layer is to prevent the waves that are outgoing from reflecting back into the corona. So this also has been done before and after us by these authors here. And a detailed description of a model can be found in this paper here. And we basically use this atmosphere. So this is for now in two dimensions. And so now we have the fluid experiment where in the laboratory, and we have this numerical setup. So what we plan to do is we want to do parallel experiments in both systems. And they have to be quantitative. So what we do is for each system, we collect an ensemble of experiments. So basically we drive the system with this parametric driving known as the Faraday excitation, as I said before. And suppose at every frequency f, suppose we fix the frequency f naught, and then we tune the amplitude A in the experiment, when we ask the question, at what threshold value of A do we start obtaining a forest of jets? So basically that means that when A is below that threshold, we don't have a forest of jets, whereas when we jack up the amplitude more than the threshold, then we start having a forest of jets. So basically, now how do we define? So basically to do this experiment, in both systems, we have to first make a definition of forest of jets, which is basically arbitrary. But as long as we keep this definition same for all our experiments, we can create a phase space out of all these ensemble of experiments. So for example, this is again that solar atmosphere in X and Z. So Z is the vertical direction, and we are basically applying a harmonic forcing, which is like this. And you will see that the rightmost one, if I run this, okay, let me first define, sorry, I didn't do this. Let me first define what is the forest of jets. So our definition is really liberal. We say that in 10 cycles of this sine omega t, in the 10 cycles, we should have at least 4 jets. And then we will say that there's a forest of jets. So it's a very, very, very nominal criteria. The other criteria is that these jets should exceed a certain length. So here we have arbitrarily set that length to be 7 megameters. So only when we have 4 jets in 10 cycles and all those jets are larger than 7 megameter, we will say that we have a forest of jets for the solar plasma. Now, similarly for the laboratory experiments, the same definition applies, but here, of course, the length becomes centimeter, 0.5 centimeter, because it is in the laboratory. But then we still need these 4 jets. So if I run this movie, you will see that when the amplitude is less than the threshold, you see this dotted line here corresponds to the 7 megameter. So none of these jets are crossing this line, so there's no forest of jets. So this particular forcing is just at the threshold. So we basically see few jets crossing this, at least 4 jets crossing this threshold. And when you have our amplitude much greater than the threshold, then of course there are several jets which are taller and more, taller and more in number as well. Then we do the same thing in the laboratory experiment where we have the Petri dish here. And again, the dotted line denotes this height threshold that needs to be crossed. So you will see here that only in these two right-hand panels does our definition of forest of jets apply. And in the ones in the left panel, there is no forest of jet. So this is done at a particular frequency. But this experiment can be repeated for different frequencies. We can just change the frequency. We have a function generator, and we can change the frequency, and we can repeat the experiments. And same in the numerical case also. So now let us put everything in this phase space, which is made out of the acceleration, the driving, the A divided by the solar gravity, scaled by the solar gravity. versus the frequency, which is also scaled by, you know, a particular value, say, 3.3 millihertz or something. Now, in both these plots, each of these symbols, closed or open triangles, they represent an experiment. So we did that many experiments. Actually, more than that, we haven't represented some more here. And for example, for some points that I'm showing, I hope you can see my arrow here. You can see that, for example, at this frequency here, so we have these experiments where we obtained a forest of jets because our A was beyond a threshold, whereas when we get below that, we don't get a forest of jets. So basically, we can draw a sort of boundary region here. So above which we will have a forest of jets, and below which we won't have a forest of jets. So the open symbols correspond to no forest, and closed ones correspond to a forest of jets. And the same thing in the polymeric fluid. Only thing is that here we have scaled it with the local the Earth's gravity. So you see that in this region 1 and 2, they have very similar behavior, very similar monotonic behavior. For example, in region 1, in both cases, they tend to, actually increase or level out with the frequency here. And of course, as the frequency becomes less and less in the solar atmosphere, it becomes more and more difficult to excite the jets because there is this critical frequency, right? So here we have this very similar phase-space relation between the two systems. So when you do this threshold acceleration versus driving frequency. So from this experiment, we basically conclude that we need a large amplitude quasi-periodic excitation in both systems. We have done this experiment with harmonic forcing so far, but if you look at P modes, for example, if you look at say P modes from SOPO or NDI data, those are quasi-periodic, and those are also able to excite jets. For example, solar convection is quasi-periodic, and that can also excite jets. But if you apply white noise, then you won't have jets. That is an interesting thing that we found out. I call this point number 3 because the first two similarities between these two systems is that both are a fluid medium and they are both stratified. I mean, there is gravity in both systems. So the first is fluid medium, and the second is gravity, and the third requirement is large amplitude quasi-periodic excitation. Okay, so now let us look at a different aspect. So suppose in plasma, of course, we cannot have a situation where there is no magnetic field, but this is a numerical experiment, so I can arbitrarily put the magnetic field to 0. And in that case, we of course don't have any jets, right? So we apply a harmonic forcing, and instead of having jets, you get these, Kelvin-Helmholtz vortices, and then everything becomes really turbulent. Whereas on in the left-hand side, you see we have applied a magnetic field, and then we are forming these coherent jets. So the idea is that this Kelvin-Helmholtz instability is breaking up the jets and making the whole system really turbulent. So if you increase the magnetic field strength, like we have done here, so you see that gradually it goes from a fairly homogeneous situation to a really anisotropic case where you have these jets forming here. Now let me show you a similar thing that is happening in nature. This is an example of large amplitude Faraday excitation, where what this crocodile is doing is essentially singing at frequency of 19 to 20 hertz, and it forms these jets. And as you see, since this is water, all these jets are breaking up into droplets. And this is basically driven by the surface tension and known as the plateau Rayleigh instability. So this also has been known since late 1800s. So Plateau did the experiment, and Rayleigh probably provided the theoretical understanding. So it's known as the plateau Rayleigh instability. But what happens when you do the same thing when you do the same thing with the polymeric fluid. So when you do this with the polymeric fluid consists of these chains, right? The polymeric chains which can extend, and these basically exert stress, and they absorb the excess turbulent energy, and therefore these droplets cannot form, because formation of droplets always needs energy, the surface energy. So these springs, the polymeric springs, would absorb this excess energy and the droplets will not form. So by the way, this this particular experiment has been done by applying P modes obtained from gong data to this polymeric fluid. Of course, I mean the gong data, from this gong data, it will be in millihertz range and this won't respond. No speaker would respond. So what we had to do is we had to make this, we basically shifted the whole Fourier transform, multiplied it 10,000 times and speeded it up, and then we applied it. But it has the same quasi-periodic frequency distribution, only speeded up. And here also you see that, this P modes from the gong data applied to this fluid also forms these kind of jets here. So now, the fact that polymer addition suppresses droplet formation has been known for quite some time. So for example, this is a jet of water, and you see that, when the jet is really at a high speed, you form these really small droplets here. But the moment you add a small bit of polymer, then this jet becomes really glassy. There are no more droplet formation. So this phenomena is because what is known as viscoelasticity. And so a basic model for viscoelasticity is this Maxwell pot model, where you have this spring, and then you have this piston, which is dipped in a fluid of viscosity eta. And this spring has a spring constant G, for example. And then when you apply some stress to it, so the spring stretches, and this piston also undergoes a viscous movement. So basically you have the elastic nature as well as the viscous nature here. So Maxwell long ago proposed that this kind of system can be represented by an equation like this, where sigma is the stress and gamma dot is the strain rate, because in a fluid you always talk of strain rate, right? So now suppose that your tau, or the relaxation rate, is very small, so you can neglect this term. Then your stress is actually equal to some viscosity times the strain rate, and you recover viscosity, so it is essentially a fluid. However, if your relaxation time is really large, then what happens is you can neglect this sigma here, and you will have tau, d sigma by dt is equal to mu gamma dot, and you can remove this time derivatives, and you will have the equation of an elastic, like a Young's modulus, right? You have the effect of what happens when you apply stress to a solid. So basically this represents a combination of fluid viscosity and solid elasticity. And often these kind of systems, in these kind of systems, we use a non-dimensional number known as Deborah number, which basically has this biblical reference that the mountains flowed before the Lord, which basically means that if you observe the mountains for long enough, they will also appear to float. So basically, if you observe something long enough, that will behave like a fluid. So if the observation time goes to infinity, things behave like a viscous fluid, but if the observation time is much smaller than the relaxation time, then it's going to behave like an elastic solid. So with this background, so let us look what more can we understand between these two systems. So there has been a lot of work way back in 2003 by Ogilvy and Proctor and Longcope as well, led by Dina Longcope as well, where they basically say that the long chain polymers, the way long chain polymers interact with thermal fluctuations of the fluid, is very similar to the way magnetic field is interacting with plasma turbulence. Essentially, I could say that the viscoelastic stress is the back reaction of the polymer chains on the solvent, whereas the Maxwell stress is coming because of the back reaction of the magnetic field of the plasma. So just like we have the MHD approximation for the plasma, where you treat in the MHD approximation, you treat plasma as a single fluid. So for viscoelastic fluids also, we have a similar approximation known as the Aldroyd V model. So there are some approximation to this model. Basically, it assumes that you have an infinitely extensible spring, which is, of course, an approximation. And the fact that the polymeric fluid is dilute, which means the chain-chain interactions can be neglected. So, which basically means that, you don't have, correspondingly in the plasma, you don't have, say, magnetic field reconnections. Now, if you were to write down the velocity equation, the equation of velocity in both systems, you can actually write it down in a very similar manner in both systems. And where, psi is the isotropic pressure, psi p and psi m, whereas sigma p and sigma m are the anisotropic stresses because of viscoelasticity and or because of the Lorentz forces. And similarly, it has been also known in the same papers and also experimentally that if you were to look at shearing flows, so shearing flows are flows where the velocity there's a so it's like the terms like duz by dx. So where the gradient of the velocity is not in the direction of the velocity but perpendicular to it. If you were to have shearing geometry like Taylor-Coit flows, then also you could write the equation of viscoelastic stress using again the Maxwell equation which I showed earlier in this manner. And similarly, you can show that the Maxwell stress can also be written in this manner here. So you see the left-hand side of both these equations look identically same. The only difference comes in the right-hand side here. And only if you have eta, which is basically the resistivity going to 0, you have the ideal MHD approximation. And you have tau going to infinity, you basically get the Aldroyd B approximation, which basically means that when tau approaches infinity, the Aldroyd B model is equivalent to the MHD model, is equivalent to the ideal MHD model, right? And it has been shown that, for this shearing geometry, the MRI, the magnetorotational instability, has very similar modes as compared to what is known as an elastorotational instability. So the elastorotational instability, essentially you have these two coaxially rotating cylinders, and you put a polymeric fluid inside it, and the two cylinders are rotating at different speeds, and then you have this elastorotational instability. So that is very similar to the magnetorotational instability. So this has been known. But no one has actually looked at what happens when you have this in the elongational geometry. So in elongational geometry, the velocity is actually changing in the direction of the velocity itself, right? So basically you have this, suppose you have a tube like this and you are straightening it. So the velocity, so there's a dvz by dz. So basically, the velocity is changing in the direction of the velocity itself. So in this case, we did not do a very rigorous derivation, but it can be shown that the stress, the viscoelastic stress, has an expression like this, where this epsilon dot is the rate, the strain rate once again, and then this TR is what is known as the Trotton ratio, which is the ratio of the elongational viscosity, the viscosity in the direction of the stretching, to the normal shear viscosity. Now for Newtonian fluids, this Trotton ratio is 3. It can be shown that it is 3, for example, for water. However, when you add polymers, the Trotton ratio becomes really, really large, which basically means that there are these springs, right? I was talking about these springs, and the springs stretch when you are elongating it, but they also are pulling the jet down because they are elastic. They want to pull it down. Similarly, in MHD, in 2D geometry, which is basically our simulation, you could write the Maxwell stresses in this form. And by comparing the eigenvalues in the MHD case to this Aldroyd B case, we basically arrived at this particular equivalence. And then we found that if we scale this with the inertial terms, the corresponding inertial terms in the MHD system and then in the Aldroid B system, we found that these two terms are actually in a very similar, have very similar values of the order of 1 to 3. So that's one good validation of the fact that maybe something like there is some similarity between MHD and Aldroid B also in the elongational geometry. Now, as I showed earlier, that these Maxwell stresses and these Aldroid, these viscoelastic stresses are basically introducing what is known as anisotropy, because the isotropic turbulence is becoming more and more, collimated or more and more anisotropic. So just by using, we basically do some heuristic calculations where we try to find out what should be this imposed vertical magnetic field that would suppress formation of this Kelvin-Helmholtz vortices. So we just do this heuristic calculation and we find that whenever the plasma beta inverse in the system is larger than the Mach number square, the formation of Kelvin-Helmholtz vortices is suppressed. Now, similarly, in case of the polymeric fluid, we find that whenever the polymer concentration is greater than this certain threshold, this threshold is coming from all these different physical characteristics of the polymer itself. Then this plateau Rayleigh instability, which is basically droplet formation, is also suppressed. So in both cases, we have the magnetic field has to be greater than a certain threshold, and on the other hand, in the polymeric case, we have the concentration has to be greater than some other threshold, and then we can suppress the instability. In one case, it is the Kelvin-Helmholtz instability, and in the other case, it is the plateau Rayleigh instability. So now it's the turn of doing this parallel experiment again. So basically what we do in the simulation is we start from B equal to 0, and then we increase this magnetic field and we count the number of vortices that are being formed, or the amount of anisotropy in the system, and we see that with increase. So this is at magnetic field equal to 0, where it's really isotropic, or there are many vortices, and then you increase the magnetic field slightly, it just drops and then it levels off, it saturates. We see a similar behavior in case of polymer. So you increase the polymer concentration a little bit, the droplet formation just drops drastically and then it levels off. So this particular phenomena is also very, so that's why I say it's a phenomenological similarity, because this behavior of these two curves of anisotropy versus the measure of anisotropy versus the magnetic field or the concentration also is very similar. So the fourth ingredient in the jet formation turns out to be anisotropy. So now from this study of very disparate systems, one is a lab system and another is astrophysical system simulated numerically, we find that there are 4 sufficient conditions for formation of jets. Now, these are sufficient conditions. These are not necessary conditions. Sufficient means this is the minimum thing that you need. If you have some more things, you can have new kinds of jets. But if you have these 4 criteria, gravity, fluid, large amplitude, quasi-periodic excitation, and anisotropy, you can easily form a forest of jets by what is known as nonlinear wave focusing and suppression of instabilities. Okay, so now we go back. So now once we establish this connection between the solar plasma and the viscoelastic fluid, now we want to find out if okay, we have been pushing the solar atmosphere with quasi-periodic or harmonic vibrations so far, which is not really what happens. So we have solar convection instead. Now we want to find out if solar convection can do this for us. Instead of us driving it artificially, can the solar convection do it? So now we add a convection zone and everything else is the same. It's just we have some convection. And then we basically drive it. And here also we get some spicules. So this is basically the movie of that. So this is a synthetic emission at 80,000 Kelvin, which mimics the silicon 4 emission of the IRIS spacecraft. And the one at the bottom basically is the SDO AIEM 171 angstrom UV emission. So you see that, and I don't know if you can see this, there are these magnetic fields which are also swaying along with the spicules. So for some spicules, we observe that, the top of the spicules are brighter in UV here. So so that needs further investigation, but this has also been reported by several observers before. So we find, so the first thing that we see is convection on its own is basically able to also produce these kind of jets which resemble solar spicules. Now these spicule tips follow parabolic paths when you do a time distance map. So suppose you watch this spicule through a vertical slit over time. So you see that the spicule tip follows a parabola. So essentially the motion is ballistic, gravity driven. However, we find that the deceleration is typically higher than the local gravity. We did not do a statistical analysis for the entire data, but for some representative samples, few samples, we found that the deceleration was higher than the local gravity. Similarly, in case of the polymeric fluid, so if you follow a tip, that also has a ballistic parabolic nature. And there also we find that the deceleration is actually typically 3 times the local gravity, the local Earth's surface gravity. Probably because of this phenomena in which the polymeric chains are pulling onto the jets. So now what we do is we take this 2D simulation. Because it's a 2D simulation, we can add millions of tracer particles to it in post processing, and we can look at what exactly the spicules are doing, what exactly the jets are doing. So here, these are all tracer particles that you see, and they have been colored by the vertical acceleration on the left-hand side here. And on the right-hand side, it has been colored by the vertical velocity. So the vertical velocity, so this color scale is a little bit different. So when you see green, it means a large positive vertical acceleration or vertical velocity. Whereas when you see yellow, it means that the vertical acceleration is negative or the vertical velocity is negative. So the first thing that you notice here is basically these green regions which are propagating upward. And these are regions of really large acceleration. So we call them acceleration fronts. And they happen to coincide with regions of shocks, the MHD, the slow MHD shocks. And basically what is happening is there are these acceleration fronts. And inside these acceleration fronts, the plasma is being speeded up. And these acceleration fronts, as they are moving upward, so gradually you get more and more plasma is being speeded up. But what happens inside the spicule is that, if you look at this fine structure, it's not that the entire spicule is moving up and then down at the same speed. So what exactly is happening is the top part of the spicule is still racing upwards, whereas the bottom part is falling downward. So there is this differential vertical velocity in these spicular jets. Now we look closely in 2 different regions. So there's convection, and we try to look at 2 different regions where the spicules are forming. One of the regions is the intergranular lanes, where you see, this there is this this granular collapse happening. So it's like, you have a hose pipe which you squeeze, and then what happens is the water squirts out. So basically that is what is happening in this region. Whereas on the region on the right here, this is just above a granule which is essentially breathing. And in the process, the granule is kicking the plasma up. And because of this kick, the spicules are being generated. So these are 2 different mechanisms, but both coming from convection, that are forming jets. But it so happens that the jets that form at the top of these intergranular lanes happen to be slightly shorter than the ones that are forming above these granules that are breathing. So now we basically take so we have the velocity and the acceleration from these tracer particles, and we just make a phase space plot of the vertical velocity versus vertical acceleration. This is for the intergranular lane, the granular lane collapse and squeezing. And on the right hand side, we have this granular breathing, which is essentially kicking the plasma. So here you see the sawtooth kind of a form, which is also known from the simulations by the Oslo group. But here we see that just above the granule, the kick is really brutal. So therefore, the acceleration is really large in the chromosphere, and therefore we can form longer spicules. Whereas, above the intergranular lanes, the acceleration is not that strong. So you see none of the data points are crossing 10 solar gravity here. So the spicules are much shorter. But then both shorter and longer spicules are essentially forming by this convective process. So basically the idea is that the convection can lead to this, high distribution of jets, even though we don't have any bimodality. We don't have you have only shorter jets and longer jets and nothing in between, but we have a, whole high distribution of jets. So recently, one of the intern students at IIA, so he basically took several simulations, 2D simulations. So these 2D simulations are really tractable because, the data is not so large, so we can handle them easily. So we had earlier performed several simulations by changing the magnetic field, and he basically put them together. And then we plot a cumulative distribution function, so which is basically the integration of this PDF over a normalized height. So it's not the it's not the exact height, but we have normalized this height here. And then you basically see that independent of the magnetic field, the cumulative distribution function looks the same. So essentially what it means is the distribution of heights, the normalized distribution of heights is same in all the simulation, irrespective of what magnetic field you have put in. So we conclude that the solar convection on its own can generate strong acceleration fronts, which can energize a forest of jets. And then we obtain this distribution of heights, which have a higher, which matches observation with a higher fidelity. Now, there's one difference that this student found, Karta found, is there is this cumulative distribution function, and then he plotted it with the actual heights in the system. And what he found is as you increase the magnetic field, there is a slight decrease in the maximum height of the spicules. So when the imposed magnetic field is less, the spicules tend to be slightly taller than when the magnetic field is stronger. So this is something he has found, but we are doing some more systematic work on this so far. So these are newer results. So let me just conclude here by saying that we did this Lagrangian tracking on the spicules which are obtained by applying a solar convection, and we found that the shocked regions in the solar atmosphere coincided with regions of very strong and focused vertical acceleration. And that gives us some insight into how the spicule plasma is energized, as this shock front is propagating upward. We also find that in a jet, this velocity is actually differential. The plasma in the bottom part is already falling downward, while the plasma at the top part of the spicule is still racing upward. So this is something I don't know if it can be observed with high resolution observations or not, but this is some prediction from our model. And finally, we believe that the solar convection in our simulation by itself can generate all kinds of spicules and therefore assemble a forest. Now, in the next 3 slides, I'm just going to give a very, very brief intro to what happens when we extend this 2D simulation to 3D, and this is what I'm going to talk about tomorrow in a seminar at INESO. So basically, this is also the work of my student Shohel. So basically, we have these solar convection, which is forcing the solar atmosphere, and you have these spicule, these structures which are rising up. And what we find is the spicules are actually could be a manifestation of this drapery structure. So basically, when you integrate along a particular line of sight, you still find that the spicules are conical. But actually, if you were to look in 3D, which the sun doesn't allow us to do really, because we are always looking at line of sight integrals. If we could look at the 3D structure, we would probably see that these spicules are part of a plasma drapery which has been folded like this. So instead of the spicules being 1D needles, they could be 2D fluted sheets. So this idea is also not new, and I think people at HAO, including field judge, had proposed that these spicules could be current sheets. In our case, they are not current sheets; they are dense regions, but they are also fluted. So whenever you do a line of sight integration, you still get jets. And then there was also another work by Anna and Matthias, where this is not about spicules, but the fact that the coronal loops could be also explained through what is known as a coronal veil hypothesis. So here, using these 3D simulation, our conjecture is that maybe spicules are also more like 2D fluted sheets rather than 1D conical needles. So last but not the least, we basically say that to explain the Poynting flux and the momentum transfer to the solar wind, it's not enough to focus on spicules, but we also need to focus on what we call the coronal swirling conduits or swirls, which are closely coupled with the spicules. So I'm not going to talk so much about it today, but these are some of the highlights of the 3D simulations that has come out. And I would like to thank you all for your time and coming here. And I would invite you to look at our paper on the 2D simulation and the connection with the polymeric fluids in this paper. So yeah, thank you for listening.
Thank you, Piali, for great talk. Very, much physical insight in this. So, any questions from the audience here as well as online? You can just either raise your hand or just speak up. Oh, okay. Oh, there's something. So we can see them again. We can see people. Yeah. Oh, yes. Okay. Thank you. So, any questions? I actually have a question. You said that you did a distribution of height of the spicules and compared to field strength. And first you said that without any magnetic field, these things break up into, droplets and fluid. So it seems the magnetic field, strong magnetic field, would give you more coherence and allow you to be taller jets. So that seems to be intuitive, that it would give you a more, because the Ionosphere is stronger. But you seem to say that the earlier view graph you said that the distribution of jets, when you increase the field
already when the field
strength increase, you actually get the jet's height.
The jet height actually slightly seems to decrease.
Yeah, that seems to be counter to the earlier argument of the.
Oh, but then I did not say that when you have zero magnetic field, I did not say that those jets, the turbulence that is going up, it is, that also, could go up pretty high, right? When it is forming droplets. So here I cannot call them jets. So I don't know what is exactly happening. But yeah, this particular, not histogram, whatever, the CDF that I plotted, this is only from the 100 Gauss to 300 Gauss. So we have not looked at say 5 Gauss, 10 Gauss, 50 Gauss. So we are right now trying to look at those fields and see if this is a monotonic decrease or there is some different dependence to it. If you will start from 1 Gauss or things like that. So
can you
that I don't know if it is monotonic or not, monotonically decreasing or not.
So you said this the deceleration is when you do this.
For few representative jets, we found that the deceleration. So on that parabola, when
the
you
parabola,
calculate this,
so the deceleration
is
greater than the gravitational acceleration. So what is the extra acceleration from? Is it the magnetic tension or what? What is?
I don't know, because the jets are there because there is magnetic field. But then there is a different study by the Oslo group, Hanstein et al. I think it is 2004. I don't remember, 2009. So there they have very shorter jets, and there they find the acceleration is actually less than gravity. And the jets are much shorter. They are like up till 5 megameter height. Whereas in our case, the jets are all more than 5 megameters, and our decelerations are also large. I don't know, how to explain these two very different lessons.
So Phil has a question. Phil, go ahead.
Hi, Piali. Thank you so much for a very nice cross-disciplinary study, a very ingenious thing. I would just like to ask you, it seems as if you must have an equation of state, some kind of implicit solution, for instance, of an energy equation or something. Is that right?
You mean for the solar case?
Yes.
You're solving the temperature equation, yes.
And does that have any, is that adiabatic or what is it?
No, it is not adiabatic.
Okay.
It has all sorts of thermal conduction, and then it also has radiative cooling, and it has all sorts of things that are normally.
Okay. Because I would have thought that I mean, if you just simply estimate the rate of energy loss from a chromospheric level in which you're doing these calculations, then typically a cooling time is about a minute or two.
Mm-hmm.
And so if you're forcing the system on a period longer than that, then this is going to lose a lot of energy. So I was just wondering to what extent you think that's realistic in what you're doing, or are you doing more, demonstrating the effects of using your LTE, etc. approximations? Do you anticipate seeing any effects there that might change the results qualitatively, or?
Even if we go to non-LT?
Yes, I mean the cooling.
Quantitative differences, but I would like to say that non-LTE is not essential to formation of these jets. So you can still form jets even if you have a simpler HAO ionization equation of state and LTE things, but then you would need non-LTE if you really want to match with observations. So the thermodynamics part, so where you are doing this forward modeling of emission, that's where you will need the non-LTE part. But to form the jets, the dynamical part, I mean, from after this work, I believe that non-LTE is not an essential part of the microphysics, is not an essential part of that.
And what kind of you're doing calculations probably with a Prandtl number of 1, right? Roughly.
Yes, yeah. But we also have tested for some other Prandtl numbers, like both less than and more than 1. Now there will be differences. There are, like I said, quantitative differences. But the fact that there are jets, especially in 3D, the fact that there are jets and that there are vortices, that part remains valid. but then, how they are interacting and, how we can classify them, how at the rate at which they are rotating. So those things might change. So often, in Hinode data, you see this bunches of spicules rotating. I mean, you also have some work where you see this. I think we have also exchanged few emails on that. So where you see these bunches of spicules rotating, and that kind of behavior can depend on the Prandtl number itself, but the fact that there are spicules and there are swirls, that does not change depending on the Prandtl number. But we have not explored the whole. We have not done 10⁻⁻⁴ Prandtl number or something like that. Maybe 0.1 to 10. That's the variation we have tried.
Very good. I'm very impressed with what you've done, and I hope you proceed to really understand more about what's going on, and I look forward to seeing further results. Thank you.
Yeah, thanks a lot, Phil.
Any more questions? Yeah.
So you said that if you drive this, the further experiment by white noise, it won't form jets, right?
Yeah, we did not see jets when we applied white noise.
So I was thinking, so it's a requirement that the driving force has some sort of coherence or some.
I mean, the FFT is not flat.
Yeah.
Right.
So I was wondering, if you increase the level of turbulence of the convection, does it break down the formation of jets?
But the convection is not white noise.
Yes. But
Convection is quasi-periodic. But even in the numerical case, when we just totally random, what is it called, this delta correlated kind of noise.
Yeah.
But all we choose a range of frequencies, and we don't get jets. So we just get this chromosphere or whatever transition region does this, but we don't see any jet formation. I don't know why. So this is very mysterious to me.
Do you think it could be some sort of resonance phenomenon?
You mean?
Because it's a requirement that there needs to be some sort of coherence or some.
Right, for these 3-wave interactions that
Yeah,
I showed, right? So you
Yeah.
have this 2 half-wave adding and giving a full wave.
Yeah.
Yeah, it could be that they're not able to add up, and when they're able to add up, something else is killing it. It could be that.
Okay. Matthias. Go ahead, Matthias.
Yeah, I had one more question regarding 2D versus 3D. You mentioned in the end of your talk, when you do these 3D radiation MHD simulations, you get something more like a veil-like structure of these jets rather than just individual jets.
Mhm.
Do you see a behavior like this also in your fluid experiments?
Yes. So we do see that. Maybe if I don't have the initial part of that.
But fluid is always 3D.
Fluid is always 3D. That's why he's asking that question. So, for example, if you look here, you see these crisped patterns, right?
Yes. Yeah.
If you're able to see, so if I sort of run it, it forms jets later on, but initially there is a curtain-like thing.
But later it turns into
Later it breaks up
fingers.
into jets, yeah. But for the sun, yeah, we see it all the time. And then when you do this line of integration, it looks really pointy. It doesn't matter from which direction you are integrating, it is still pointy.
Mm-hmm.
Bill?
Yeah, this reminds me about a question of whether the magnetic field is an active or passive part of the dynamics that you see. And I'm getting the impression in the last year or two, in which I've been studying a lot of different things, that in fact the magnetic field is often the large scale observable magnetic field serves only to define the local topology, connectivity, and to define the Alfvén speed. But it doesn't look like the Alfvén speed is relevant here. It's just field aligned motions and shocks and what have you that are generating these things.
Yeah,
Is
yeah,
my picture right?
I agree with you because when I showed this Lagrangian tracking things, so there I could actually look at these quarks and color them with the Lorentz force, and I don't have that plot here, but I found that
Yeah.
the Lorentz force is contributing much less than the the other forces, the
Yeah.
whatever other forces are there. So the Lorentz force, there is magnetic reconnection above the below the taller jets, but that reconnection is only serving to let the fluid pass through. It is not providing any additional kick, or the kick is much weaker. That is what I find.
Yeah.
Don't have
Yeah.
it
So
here,
so
but
I've come to the same kind of conclusions from very, very different point of view with regards to coronal heating. And I remember Peter Sturrock wrote a nice paper in 1999 asking in his abstract, is the magnetic field active that we observe or is it really passive? And I'm really coming to the conclusion that things are actually very passive, and that things like large scale or observable scale reconnection have very, very little to do with actual heating.
yeah, but one thing to remember is my simulations don't have flux emergence. So
Absolutely, that's what's needed though to generate flares and stuff. So
but
somehow,
but regions where you have flux emergence, there people can have this this whiplash effect and that sort of thing. But we don't have that.
yes,
Because there
yes,
is no flux emergence. It is like in the coronal hole region where there would probably be some flux emergence, but not so much.
yeah. Well, thank you so much. Do you is the talk tomorrow being shared online?
It's
It's in
I
an
was given a
envelope.
Zoom link,
Yeah,
so I
there's a
can
Zoom.
pass it to you if you.
Okay, that would be great.
1
Thank you so
o'clock.
much.
1 o'clock. It's at
Yeah,
1
1 o'clock
tomorrow.
tomorrow, and that's all.
Yeah.
Okay, great. Thank you.
Okay, so
Thank you.
yeah, Piali will be here till
Friday.
Friday morning. So she's gonna talk to her. She's on the 3rd floor. So let's thank the speaker again. Thank you.
Thank you.